Good morning, everyone. And this week we will talk about the work done by an electric field. We'll also introduce the electric potential energy and the electric potential. And then we will show the equipotential surfaces and how they interact with the electric field that is generated by electric charges. So we have seen earlier that we can calculate the electric force exerted on a charge that does exist in electric field using this expression, F as a vector equals to QE. Looking at the charge here, I can conclude that the sign of this charge will decide on the direction of the electric force. So if this charge is positive, then the force will have the same direction as the electric field. If this charge is a negative charge, then the electric force will have an opposite direction of the electric field. Okay, so as we can see here, this is a positive charge in an electric field, and this is why the electric force exerted on this charge is in the same direction of the electric field. Here, because the charge is negative, the direction of the force is in opposite direction than the electric field. So if we have a point charge, then the electric field generated by this point charge is as simple as K charge divided by R squared times R hat. So whoever decides on the direction of the force is basically the direction of the electric field, either in the same direction or in the opposite direction. If we have here an electron, that this proton who's exerting this, who's generating this field, is exerting a force on this electron, then definitely the direction of the electric force exerted on this electron will be in the opposite direction. Why? Because that's an electron. Now, if I look here at the electric field due to the line, an electric field due to a line of charge here, we have derived the relationship for the electric field before. So, for example, if I have an electric field, this is the line of charge that is generating this electric field, and I have an electron that's sitting right here. Then this electric field is given by, this is a positive charge. Then the electric field generated on at this location is pointing upward, and the electric force exerted on the electron, because it's a negative, would be pointing in this direction. And we can conclude this from this expression, where this is the electric field due to the line of charge times the negative charge for the electron. Then this gives me a force that is in the opposite direction of the electric field. Now let's look uh, at the electric field induced due to an infinite sheet. An infinite sheet can be derived from the electric field due to a disk of charge by having the radius of this disk goes to infinity. So in this case, if the radius of this disk goes to infinity, in this case, I will be generating an electric field on this sheet of charge that are perpendicular on the sheet of charge because the electric field right here at this location close to that sheet would be uniform, and that's why you can see that the electric field is uniform on this infinite sheet of charge. So we have this is the case we derived the infinite sheet of charge from. If you recall, this is the electric field we derived by applying the integration. Now, if you take this radius of this disk of charge to infinity, which is a in this case, this is going to result into this is infinity. This one would be negligible, which means 1 over infinity will go to 0, and then h will cancel with h, and then you'll end up with k sigma 2 pi k hat, and then if you substitute k Coulomb's constant with 1 over 4 pi epsilon naught, then the 2 pi would cancel, and you will end up with this electric field for one infinite sheet of charge, either on top or at the bottom. The electric field, because this is a positive charge here in this case, will be pointing away, and it will be uniform at the areas close to this sheet. So it will be uniform here on the top and uniform here at the bottom as well. As you can see, the directions is in the opposite direction because it is pointing away in both cases. Now, those are two questions. I'll leave them to you to solve those questions, and then we can check the answers together in the live sessions. But I'll leave those to you to solve them on your own. Then we'll go to the parallel plate capacitor. So in the previous slides, we introduced the electric field due to the infinite sheet, and at that case we found that this electric field equals to sigma, which is the surface charge density, divided by 2 epsilon naught. I'll take this one as the magnitude. So here in this case, if if I bring now two infinite sheet of charges, one of them is negative and one of them is positive, and I bring them close to each other. In this case, the electric field outside, because those are uniform electric field, and we assume that we are at the region where the electric field is still uniform. So ideally, the electric field outside here would cancel because they are uniform. One of them is pointing to the left, the other one is pointing to the right. So ideally, at outside would cancel. Inside, in between, they will be they will add up, and that's why you can see that the net electric field is also uniform everywhere between those two plates of the capacitor. So in this case, if we have the electric field, the red one here is sigma over 2 epsilon naught, and the blue one is also sigma over 2 epsilon naught. Then if you add them, in this case, the E net, which is the magnitude here, would be sigma divided by epsilon naught. By adding those, which basically means you're multiplying them by 2, you will end up with a net electric field being sigma over epsilon naught. So this is what we have just introduced. If I am to introduce the electric field as a vector, it will be always pointing in the direction from the positive charge toward the negative charge. So if I have my coordinates are being this way, or here we have it as a k. So this is, let's assume that this is z, this is y. In this case, the electric field would be pointing from the positive toward the negative, and in this case, the direction of the electric field would be k hat in this case, and the magnitude is sigma over epsilon naught, the one that we have concluded in the previous slide. Now, this is here ideally, the electric field is here, as I said, zero ideally, and no electric field right at the edges. This is an ideal approximation for the electric field between two plates. However, in reality, it will not be zero because there will be a finite distance where the electric field now start to change, and that's why here will be greater from the negative more than the positive. That's why it will be pointing inside toward the negative here, because this region is closer to the positive than the negative. Then it makes sense that the electric field here is a bit stronger than the negative, and that's why I do have a net electric field. And here at the edges I have a fringe field where basically the electric field will tend to curve at the edges going from the positive toward the negative. Again, this is the real representation of the electric field within the capacitor. But for us, we will be dealing with the ideal case. But this is just to give you an idea about the difference between the reality and the ideal case. So where did we see those two plates that are generating uniform electric field in between, that will be using to uh, divert a beam of charges? And the cathode ray tube, the one that we used to use in TVs long time ago, we have here, uh, as you can see, two parallel plates that are horizontal and two parallel plates that are oriented in a vertical. The purpose of those two parallel plates is to induce electric field in between, to apply forces on the uh, beams of electrons that is directed toward the screen. Remember, if we have a charge and this charge has been put in an electric field, then this charge is going to face an induced electrostatic force on that charge. And this is how we used to utilize those fields to generate induced forces to divert those beams of electrons in the direction that we are interested in. So how does this happen? If I have here a positive charge uh, plus 2e, and then I let this charge come and go through an electric field, a uniform electric field, which of the following figures correspond to a correct illustration of the resulting trajectory of the alpha here, that is called alpha particle? the field directed upward as shown. So we have the electric field pointing upward, as we can see here, and we have an alpha particle that has that is an ion with a plus 2e charge, and it's going, as you can see, coming perpendicular on the electric field. Which one is the correct representation for the resulting trajectory of this particle? We can see that this is a positive charge. This positive charge will be attracted toward the negative plate of the capacitor. We know that the electric field starts from the positive, goes toward the negative. So this deflection upward is the correct one. So in this case, it will be either this, this, this one is wrong. Why? Because this uh, uh, positive charge will never be attracted toward the positive, will be attracted toward the negative. So this is wrong. This is wrong. Here, there is no attraction at all, which means there are zero force applied on it, and we know that there are forces applied on it. So this is wrong as well. This one has it deflects with a 90 degrees, and this never happens because it in this case this means that the velocity became zero in this direction, and this is wrong. So we end up only with two figures, either A or B. Which one is the correct one? Now we know that once this particle enters the electric field, it is going to be under the influence of an exerted force on this charge. What's the direction? Well, since it is positive, then it has to be in the same direction as the electric field. So it will be positive pointing upward as well. Now, what's this force going to do? This force is going to now apply an acceleration on this particle, which basically causing it to develop a velocity going upward. So this velocity is continued to go to be, increasing till it reaches this point. At that point, when it leaves the field, there will be no force, and then this charge is going to continue with its final velocity that developed right at this point. This one is wrong. Why? Because this means that the force is still there and it keeps curving, and this is not correct because the force is ending right at this point. Right after this point, there are no forces applied on the particle, and the particle should continue with the velocity it developed right at the last point. It has the it had the force applied on. So in this question, we need to know that's an electron going through this electric field. This is a uniform electric field, and the question is asking, it's coming with a velocity v naught, and the question is asking what can we say about the magnitude of the velocity of the electron Vf as it exits the region containing the electric field on the right. Remember, we said that this particle is going to have a force exerted on. So this is an electron. So once it enters the field, this is an electron, there will be a force applied in the opposite direction. Why? Because it is an electron. So the, the force applied on it will be in the opposite direction of the electric field. So now it's starting with a zero velocity. Once there's a force applied on it, then this electron is going to start curving till it reaches this point. At this point, it has the v naught velocity here, horizontal, and whatever it has developed, v, we call this one vertical. And in this case, the total velocity would be the summation of those two, which is Vf. So if we look at the Vf, definitely the magnitude for the new velocity right at the end when it exits the electric field should be greater than the initial velocity, which is v naught. So v naught is not changing. V naught, the horizontal stays the same. However, the particle will start to develop a vertical velocity, and the summation of those two velocities is vf. And in this case, we know that vf is greater than v naught. Now, the work that is carried by a force basically equals to that force dot the dot product of that force with the displacement vector. So if I have an object and this object is under a force F and this object has moved from one position to another with a displacement vector delta r, the work is as simple as the magnitude of the force times the magnitude of the displacement vector times the cosine, the angle in between. So for example, in my case here, I have the angle between delta r and f being zero because they overlap, which means that cosine zero is 1, and this is the work done by the force F on this object that has moved with a displacement vector of delta r. Now, the work kinetic energy theorem states that the work that was done will cause a change in its kinetic energy such that this work that has been done equals to delta k, and this delta k is indeed the kinetic energy of the final destination minus the kinetic energy of the initial state. The final state minus the initial state. So this work that the force has done to go from point A to point B is also equal to the electric potential energy at point A minus the electric potential energy at point B. Or if I am to write it in delta, then I have to make it as initial. If I take the minus outside, then this becomes UB minus UA. The initial the final minus the initial is the delta, and that's why now this work equals to minus delta U. So we know now that the work equals to the difference in the kinetic energy between the final state minus the initial state equals to minus delta U. So the electric potential energy is in concept is the same of what you have seen in earlier physics courses when you studied uh, the gravitational potential energy. Here is the same as we will see later on. The charge that does exist in an electric field always tend to go toward decreasing its electric potential energy. If you let go inside the field, the force exerted on it will always go in a way such that this charge or that particle that is charged is always goes toward decreasing its electric potential energy. Now, this potential energy only work on conservative forces, like, for example, the gravity. However, potential energy does not work on non-conservative force like a friction, because this friction will end in power loss or an energy loss that you cannot retrieve. However, when it comes to conservative force like the gravity, for example, you can always go back to to the initial potential energy by applying a force in the opposite direction. So we will be dealing with the conservative forces, and in this case, we have the conservation of energy, which basically says that the delta K equals to minus delta U. Delta K equals to minus delta U, assuming we have a lossless system. In the absence of non-conservative forces, I have no losses, no friction. I'm talking about a lossless system. In this case, my energy would be conserved. An ideal system, for example, to make our study easier. Okay, so if we have this positive charge that has a mass m that is placed in this uniform electric field, what is the work done by the electric field if the charge undergoes a vertical displacement delta r down? So let's look at this charge. This charge is moving delta r down this way. So let's see. In this case, this positive charge is the work done by the electric field would be F dot delta R, right? And as you can see, F is pointing downward as well. If I am to look at the F is also pointing downward, which means that F dot delta R equals to F magnitude times delta R times cosine theta, which is theta here is zero because the force and the displacement vector overlap, which means this one is one. So here, if this distance is d, so if delta r is d, and I have f as a qe as well, then the work done would be qe d. So work done by the electric field on this charge is QED. If the charge starts from rest, what is its speed after moving this distance? Now remember, what did we say about the work? The work equals to delta K, which is the final destination minus the initial was zero, starting from rest. Then if the work is a QED, then QED equals to half v squared, and v is the final velocity or final speed. What is the change in the charge's electric potential energy? Now, back to the change, which is the delta U. This delta U is minus delta K. And I know delta K is half mv squared or QED, they're equal. Then my difference in the electric potential energy is minus delta K if I want to represent it in the kinetic energy, or minus QED if I want to represent it as a work. Why? Because delta U equals to minus delta K or minus QED in this case, because delta U, as we can see, is minus delta K, and delta K is QED. Okay, so we said in electric potential energy in a uniform field, we have seen that the parallel plate capacitor is a special case where we can get a uniform electric field, and in this case the electric potential energy can be expressed in this form that we have seen earlier, that is delta U equals to minus QED, where this is the magnitude of the electric field, and basically this is no difference than what we have seen earlier in previous physics courses, where the difference in the potential energy, gravitational potential energy, equals to mg delta y. So with the points that we have seen earlier when we started this course, that opposite charges attract, like charges repel, electric field points away from positive charge towards negative charge, and forces, if the charge that I'm evaluating the force on is positive, then the force is in the same direction of the electric field. If that charge is negative, then the force is in the opposite direction of the electric field. Now we have another point to add to, which is a particle on its own, if you let it go in an electric field, will move in the direction which lowers its potential energy. Electric force, as we said, always points toward lower U.